invitation. It's my first time in Poland. Wonderful so far. So please stop me if you have any questions. So these lectures are going to be about geometry of polynomials, which I'll say what that is in a minute, but really it's going to be about geometry of polynomials and graphs, which is a topic that's obviously very important in computer science. This is the computer science series of lectures. And so the general paradigm that I'm going to discuss in these lectures is I'm going to talk about various problems concerning graphs. So we'll be interested in, we all know what graphs are, finite, undirected, simple graphs. And we'll discuss various problems concerning classical combinatorial structures like matchings, spanning trees, and cuts in the graph. These are all things of interest in computer science. And what these lectures are about is this paradigm where we encode these discrete objects, which are graphs, as some continuous objects, namely polynomials. And somehow we'll be able to solve all sorts of interesting problems on this side by encoding graphs as polynomials and studying these polynomials. And we're going to study them. Polynomials are an incredibly general object that occupies a vast area within math, but specifically we're going to be interested in the following very high-level idea, which is if I have a polynomial, so let's say I have a univariate polynomial p of x, I can actually think of it in at least 3 different ways. So the usual way is I can think of it as just in terms of its coefficients. So let's say it's a degree n polynomial. Let's say the coefficients are maybe real or complex. Okay, so that's the most obvious representation when you think of polynomials. But then, you can, when these are complex, you can factor this polynomial. You can also think of this as a product of linear factors over the root. So these are the zeros, also over the roots. And finally, you can also just think of such a polynomial as a function from complex numbers to complex numbers. You have these 3 different representations of the same object. In general, it's not it's not easy to go from coefficients to roots. That involves finding the roots of a polynomial. So you can do that up to degree 5 with a formula, but in general, this is not something you can explicitly solve easily. But the theme of this course is that for various nice classes of polynomials, even if you can't exactly find the zeros from the coefficients or vice versa, if you know something about the coefficients, you can deduce something about the zeros and vice versa. So what do I mean by that? So here's the simplest example. The simplest example is, let's just consider the quadratic polynomial ax squared plus bx plus c. Okay, so quadratic is easy, you can actually solve for the roots. But what are some nice relations between the roots and the coefficients? Well, one is that the zeros are real, so that's a property of this side, if and only if a certain inequality is satisfied by the coefficients, namely the discriminant is non-negative, right? If and only if b squared greater than 4ac. Okay, so this is the type of connection I mean. If you know something about the zeros, you get some information about the coefficients without necessarily solving. Another sort of basic observation is, suppose the coefficients are all non-negative. Well, this implies, in one direction now, that there are no positive zeros. Okay, so these are some high school level facts. And basically what we're going to do is we're going to study this interplay between zeros and coefficients. Facts that are essentially generalizations of these kind of facts and prove some interesting theorems about graphs. So that's a very high level outline of the course. And on each day I'm going to cover a different combinatorial application. So today, so by the way, geometry of polynomials, maybe I should just say what it is. It's a sort of classical small subfield of mathematics that refers to the analytic theory of zeros of multivariate polynomials. So one thing I should mention is, here everything I've written is univariate. We'll also look at multivariate polynomials. That's what the first part of this title refers to. And somehow the key point is the focus is on inequalities and analysis. This is not algebraic geometry. That's what distinguishes it from algebraic geometry. Okay, so let me start by giving you sort of a warm-up application. So I'm going to talk about matchings in graphs and their connection with real-rooted polynomials. Any questions so far? Okay. So suppose I have a finite graph, and suppose it has an even number of vertices. So I want to look at the matchings in this graph. Okay. So matching is just, it's a set of edges where no two edges share a vertex. And what I'm interested in is the numbers of matchings of different sizes. Okay? So I'm going to let M0 be the number of matchings with, I'm going to let Mk be the number of matchings in G with K edges. Okay, so the vertices are labeled 1 through n, let's say. There's some finite number of matchings of various sizes. These MKs are just going to count them. So in particular, okay, M0 is just 1, M1 is just the number of edges, because every edge is a matching with one edge. And this is going to go up to n over 2, potentially. Now, the graph has n vertices, so a matching with n over 2 edges is a perfect matching. So m sub n over 2 is the number of perfect matches. Okay. So one sort of classical combinatorial question that I want to examine is, how are these numbers related to each other? How are the numbers of matchings of different sizes related to each other? So if you go on your computer and just pick some graph and plot all these numbers, so the question is, how are these MK related? That's a vague question. But if you go on a computer and plot them, so if you plot M0, M1, M2, you'll always see a sequence of numbers that's first increasing and then decreasing. You'll always see this. Okay? So this is what's called the unimodal sequence. And the first theorem I want to prove to illustrate this paradigm is a theorem that I'm going to call theorem U, which is originally due to Heilman and Lee, 1972, I think. And the theorem says that for every graph G, the sequence of matching numbers, or maybe let's call it like this, is unimodal. And what that means is that there exists some index L such that these numbers are first increasing up to this L, and then they're non-increasing. So this is U for unimodal. So this is the first theorem I'm going to prove. So are there any questions about the statement of the theorem? Okay. Okay? So to do this, I'm going to follow this paradigm that I have some question about graphs, and I'm going to turn it into some statement about polynomials, and then use this kind of use this interplay to study these numbers. So let's turn these numbers into a polynomial. There are many ways of doing this. You can make all kinds of generating functions. Let's just try the simplest one. So define, so you fix a graph G, okay, and define m sub g of x to be the univariate polynomial whose coefficients are just the m sub k, the matching numbers. So I have k going from 0 to n over 2, and I'm just going to have x to the k and k. So I'm going to call this the matching generating function. Okay, so later on we'll see something very closely related that's called the matching polynomial, which is, it's not quite this, but I'm just going to call this a matching generator. Any question?
Notation, MQ?
M sub G, sorry, so for the graph G. So given a graph G, let M sub G be this polynomial. It's a degree n over 2 polynomial. Okay. So the main theorem I'm going to prove in this lecture, which will occupy most of the lecture, is, by the way, is this visible or is this too low? Okay. So I'm going to prove something that I'll call theorem R, which is just that this always has all real roots. Okay, so that's not at all obvious right now. I've just made a polynomial with these combinatorial numbers as coefficients. But it turns out that mg of x is real rooted. That means all of its roots are real. Okay. Okay. So first of all, it's not clear why this would be the case. But secondly, it's also not clear what bearing this has on the original problem, right? On theorem U. It seems like a totally unrelated statement. So first what I'll do is I'll explain how theorem R implies theorem U, and then I'll prove theorem. Okay, so good. So let me now say a bit about real rooted polynomials. So I'm going to say real rooted a lot, so I'm just going to refer to it as R. I'm going to write it as RR for real rooted. Okay. So why is this good? So let's list some properties of real rooted polynomials. Okay, so here's one property, which is kind of easy to check, which is if p of x is real rooted, then if I reverse the polynomial, let's call it rev of p. This is the polynomial x to the, okay, so let's say this polynomial is of degree n. If I have a degree n real rooted polynomial, then if I reverse it, so that just means I look at this polynomial, I just literally reverse the coefficients. This is also real rooted. Okay. So this is literally, I mean, if p is summation x to the k a k, then the reversal is literally the same thing, but it's x n minus k. Okay, so can anyone see the proof of this? Okay, so the proof is just, well, assume this has a complex root. That root's not 0, because 0 is not complex. So then 1 over that root is the root of this. That's not real. Okay, this is sort of easy property. Okay, let's move to a slightly more interesting property. The second property is if p of x is real rooted, then its derivative is also real rooted. differentiation preserves the property of being real rooted. Okay, so this has several proofs. Maybe the easiest proof is just use Rolle's theorem. Okay, so if it has n zeros, then between every two zeros there's a critical point, and so on. But let me now give you a different proof that instead of using real analysis, uses complex analysis. And this is a proof of what's called the Gauss-Lucas theorem, which is a more general statement that will be useful later, and also explains why this field is called geometry of polynomials. So this is maybe the first theorem in this field ever. I don't know where it's from. I think Lucas actually proved it like 100 years before Gauss or something. But anyway. So the Gauss-Lucas theorem is a stronger version of this, and here's what it says. It says that the root of the derivative of p, let's call it p prime, these are contained in the convex hull of the roots of p. For any complex univariate polynomial. Okay? Okay, so this is a statement about real rooted polynomials. This is a statement about all complex polynomials. So it says if you differentiate the polynomial, the new zeros are in the convex hull of the equal zeros. And this immediately implies this theorem, right? Because the roots are real, the convex hull is also real. So this implies this theorem. How many people already know the proof of this theorem?
Sorry, maybe you could explain what convex hull is, because maybe
okay, sure.
Maybe not everybody.
Okay, so let me just draw a picture. So this is a polynomial with complex coefficients. It has some roots in the complex plane. Let's say lambda 1, lambda 2, lambda 3. So let's say p is degree 3. The convex hull is just, it's a set of all convex combinations in the complex plane. So it's the smallest convex set containing these points. Okay. And then what the theorem says is when you differentiate the polynomial, you'll get some new zeros which have to lie inside this convex hull. You'll only get 2 because now the degree is 2. So this is why it's geometry. This is, it's a two-dimensional geometry, right? There's this, is that clear? Does anyone have? Okay. Okay, so let's prove the Gauss-Lucas theorem. Let's prove it over here. So there's p and then there's p prime. I want to show something about the zeros of p prime. So let z be a zero of p prime. Okay? Now if z is already a zero of p, then it's obviously already in the convex hull. So let's assume it's not a zero. And now let's factor p. Okay, so by the fundamental theorem of algebra, I can factor this. Okay, so there's a leading coefficient here. Let's assume p has degree n. Z? Okay. Oh, I'm sorry, z. X. Let's make this x. I made the variable x. So okay, z is a specific point. Z is a point in the complex. Okay. Okay, let's assume without loss of generality that this is 1. None of this is going to change if I scale the polynomial by a constant, if the roots don't change. So now, what am I going to do? I'm going to look at this rational function, p prime of z over p of z. I'm going to look at this ratio. Okay, so z is now a specific. Okay, so this is on one hand, this is 0, because this denominator is not 0, the numerator is 0. On the other hand, I factored this, so if I differentiate it, what do I get? P prime of x is, by the product rule or whatever, it's a sum of all n minus 1 y's products of these things. I don't want to write it, but okay. But now when I divide these things, this has a very nice form. This is summation I less than n 1 over z minus 1. Because so 0, I've expressed this rational function. This rational function is 0 at this point z. So now, okay, z is not a 0 of p, so these are all not 0. It makes sense. So now I can just multiply it by the conjugate. Okay, so now what does this tell me? So this denominator now is the squared magnitude of this complex number. And if I rearrange this, I guess I can use this board. So if I rearrange this, so this denominator I can write as magnitude of this complex number squared. And now, okay, I can separate out these bars. I can move the z bar to one side. I get that z bar times summation 1 over z minus 1 squared and squared is equal to summation I squared. Okay, but these are now just some positive numbers, right? The 1 over the magnitude. So now I have that z bar is equal to a weighted sum of the lambda bars with these weights. Okay, but I can remove the bars. These are real. The bars don't change, and that's a convex combination. Okay, so that's the proof of the Gauss-Lopez. So any questions about this? Okay. So that's one good property of real-rooted polynomials. We're going to use this later in the course too. That differentiation preserves real-rootedness. And finally, I want to use these two properties to prove some important inequalities that are called the Newton inequalities, which are a generalization of this b squared greater than or equal to 4ac in a certain sense. The third thing I want to prove is called the Newton inequality. I suppose this was proven by Newton. Okay. So the Newton inequalities, what they say is that if I have a real-rooted univariate polynomial, if this is real-rooted, then the coefficients actually have to satisfy certain inequalities. This makes sense. I mean, not all polynomials are real-rooted. There are actually some very clean inequalities. then you have the AK over N2's K squared is at least AK minus 1. So if you take the coefficients and normalize them by the binomial coefficients, for any coefficient, its square is bigger than the product of the two neighbors. So this assumes real rootness. Okay, so let's prove this now. So what's the proof? Well, okay, so this is true for every k, by the way. Okay, so this will be a part, right? So for every coefficient, this is true. Every coefficient, okay, it doesn't make sense for the ones at the ends. Every coefficient not equal to 0, right? Okay, so what's the proof? Well, so fix some k. So what does the polynomial look like? It looks like this. So I have these three coefficients somewhere in the middle of my polynomial. That's what the polynomial looks like, right? This is real rooted. Okay, so I somehow care about these three coefficients. So what can I do? I can differentiate this k minus 1 times. Why not? What's that going to do? Well, it's going to kill everything after this term, because it's degree less than k minus 1, and it's going to introduce some binomial coefficients here. So let's write down what those are. So here you're going to have n minus 1, and you're going to do this k minus 1 times, you're going to have n minus k plus 1, a n x to the n. And then I'll get some stuff. Here again, you get some binomial coefficient. I mean, okay, we get some binomial coefficient that I don't want to write. A k plus 1 x squared. Some binomial coefficient, a k x. And here the binomial coefficient is just k minus 1 factorial, a k minus 1 plus 0. Right?
It's n minus k the power.
Is it n minus k?
No, the exponent.
Oh, I'm sorry, n minus. So you differentiated k minus 1 times, so it's going to be n minus k plus 1. Thank you. Okay, so if you differentiate it a bunch of times, certainly the degree goes down. It's still real rooted though, right? By that property over there. Okay, so now what am I going to do? I'm going to reverse it. Is there something wrong with what I've written?
The coefficient is probably n minus k plus 2.
Okay, so let's see. So I want to differentiate it k minus 1 times. So I should have n minus k plus, I should have k minus 1 terms here, right? Am I off by 1?
Yes.
Okay, what should this be, n minus 2?
Plus
2, okay. Okay. So, yeah, please watch my binomial coefficients, because it's not the sort of thing I'm good at, but, okay. So, so you get some binomial coefficient. Okay, now, you reverse the polynomial. I don't want to write the whole thing again, but it's still going to be real good. And now, I'm going to differentiate it again to kill off these terms. Okay. So now I'm going to differentiate it n minus k plus 1 times. Or whatever is required to kill off these terms. Right? so I differentiated it here to kill off these terms. Then I reversed it. Now I'm going to differentiate it again to kill off these terms. Okay? And what do I get in the end? I only get 3 terms, right? The only terms that survive are these 3. And you get a quadratic polynomial whose okay, you get ak plus 1 x squared, I'm sorry, ak plus 1, because I reverse, plus some binomial coefficient times akx, plus some binomial coefficient times ak minus 1 x squared. And that's a quadratic real-rooted polynomial, right? I preserved real-rootedness in all these steps. So what did we say in the very beginning about quadratic real-rooted polynomials? B squared greater than or equal to 4ac, right? So if you actually do this and figure out what B squared greater than or equal to 4ac is, it's this. You can imagine there are some binomial coefficients. So okay, these little observations led us to proving this actually quite important inequalities that are called the Newton inequalities. And in the case of n equals 2, this is b squared greater than or equal to 4ac. You can check, right? 2 choose 0, 2 choose 1 is 2, 2 choose 0, and 2 choose 2 are 1. Okay. So I should say this is implied by real-rootedness. For n equals 2, this is equivalent to real-rootedness. For n equals 3, it is not equivalent to real-rootedness. Okay? This is known. Maybe this will be one of the exercises. This is not equivalent to real-rootedness. Okay. So now let's get back to what we were doing and see why we're happy, right? So we had this little foray into real-rooted polynomials with roots of elementary properties. And now we can quite easily see why theorem R implies theorem U. Okay? So why is that? I'll just erase this. Okay, so now you have proof of theorem U, which is the theorem about unimodality of these matching coefficients. Well, what's the proof? Well, by theorem R, this is real-rooted. So this polynomial is real-rooted. So then by the Newton identities, namely property 3 that's written over there, I get that these coefficients satisfy these inequalities. Sorry, minus 1. By the way, these inequalities are called ultra-log concavity. That's the bug. Okay. So Newton inequalities imply that these are ultra-log concave. Okay, and then it's an easy exercise to see that, well, in particular, this implies that this is true without the binomial coefficients. If you just expand these out, you get that this ratio actually bigger than 1. So you get that mk squared is bigger than mk minus 1 times mk plus 1. So this is true for all k except for the endpoints. Okay. But this actually implies unimodality. Because, well, imagine what would happen. Suppose you didn't have unimodality, so this is our picture here. If you didn't have it, then at some point you would have a dip. Right? And then at this point, you would have that AK is less than AK minus 1 and AK is less than AK plus 1. One of those inequalities has to be strict. And that's not possible. Okay? So that proves theorem U. As far as I know, this is actually the easiest way to prove theorem U. So this is a common theme in this area, that you have some combinatorial property like unimodality. There's like a whole research area around proving sequences are unimodal. And it's surprisingly hard to prove it. It's not, often to prove a relatively weak property like this, you have to prove something much stronger, like ultra-log concavity, which you then have to prove with something even stronger, like real rootedness. Okay? So this is kind of surprising, but it's one of these. I mean, combinatorics is hard, and anything but combinatorics is easier. So, yeah. Okay. So, any questions about this so far? I haven't proved theorem R. That's what the rest of the lecture is about. But yeah, this was I mean, basically from these facts about quadratic polynomials and differentiation, you see that real rootedness implies. Okay. So now what I'm going to do is prove theorem R. That's what the rest of the lecture is going to be about. Okay, so to prove theorem R, I'm going to need to do something even stronger, which is I'm going to actually need to pass to multivariate polynomials. Okay, so this is a univariate polynomial in one variable, but another sort of somewhat counterintuitive thing in this area is often when you want to prove that a univariate polynomial is real rooted, you instead have to find some multivariate polynomial that is real rooted, which I'll say what that is in a moment. Such that the univariate polynomial is a restriction of that polynomial. So this brings us to the concept of real stability, which is a multivariate generalization of real rootedness. Okay. And the reason for passing to real stability is, so in this proof, what was really important is that we identified some nice operations that preserve real rootedness. Differentiation, reversal, and so on. It turns out if you look at multivariate polynomials, you have a much larger class of operations that preserve whatever this notion of real rootedness is. So introducing more variables gives you a much richer class of transformations is the high level idea. But okay, let me just say what real stability is. So let's define it. So now I have a multivariate polynomial in n variables. Okay, previously n was a degree, now n is the number of variables. Okay. So this is, it's going to only have real coefficients. No? So a polynomial, a real polynomial in n variables is real stable. So I'm going to use RS to mean real stable. If it has no zeros with all entries, it has no zeros with all coordinates in the upper half of the complex plane. Okay, so if P of Z1 to Zn is not equal to 0, whenever the imaginary part, I'll just write it like this, whenever Zi is in the upper half plane for all I. Okay, so what's the upper half plane? Maybe I'll just write it. The upper half plane is the open upper half complex plane. So it's a set of all numbers with strictly positive imaginary part. Okay. That's the definition of real stability. It looks a little weird, but I'll show you a bunch of examples and you'll see that it's actually quite nice in a moment. And I have to add one more case, or it's identically zero. It's convenient to assume the zero polynomial is real stable. This is, you can do it, you can also not do this, but then you have to keep it writing. Okay, so that's the definition of real stable. So I said this is a generalization of real rootedness. So first let's check that it actually is a generalization. Okay, so case of one variable? Well, okay, so suppose P of x is real stable. Okay, what does this mean? This means that P of z is not 0 for all z in the upper half plane. So P has no roots in the strict upper half plane. But this is a real polynomial, that's important. So the roots appear in conjugate pairs. Okay? So then this implies P has no roots in the lower half plane, the open lower half plane, you can imagine what that is. And then that implies P is real rooted. And okay, these are all economic. So that's why I needed the coefficients to be real. Okay, so the n equals 1 case is just real rootedness. Let's maybe look at some examples. So what are some examples? Well, one example is, I don't know, just any monomial like this. That's not going to be 0 if everybody's in the upper half plane. Here's another more interesting example. Let's look at the polynomial 1 minus x1 x2. So why is this real stable? So this is my P of x1, x2. Okay. So now, okay, this is the complex plane, this is a real line. Suppose I have two complex numbers in the upper half plane, z1 and z2. Okay. So their argument is going to be strictly between 0 and pi. Right? So we have theta 1 and theta 2. And so now, if I multiply these numbers, so this is the upper half plane. If I multiply these numbers, the arguments are going to add up. And what I get is that the argument of z1, z2, which is going to be the sum of these angles, this can never equal 0 or pi. Because they're both strictly in the upper half plane. There's no way to multiply these two things to get, oh, I'm sorry, what am I saying? Not 0 or pi. Cannot equal 0. Right? Because the worst thing can happen is these are both just, okay, they're both really close to pi. I multiply them together, they end up here. But they're never actually going to be positive real numbers. Okay, I'm just saying they're not positive real numbers. Okay. But then that means this cannot be 0. Right? So this is an example of a real stable polynomial. Maybe a non-example is the polynomial 1 plus x1. Right? Why is this not real stable?
Minus I.
You just plug in I. Okay. What else is there? Okay, so those are some examples. I want to mention one more geometric way of thinking about real stability. Maybe I'll write it here. So here's an equivalent definition. It says a polynomial p in some vector variables x if and only if, for every vector A in the positive orthant, strictly positive orthant, and for every vector B just in Rn, this restriction, so T goes to P of PA plus B. So this is a univariate polynomial, right? T in one variable T. This is real root. Okay. So the equivalence will be an exercise maybe during the class tomorrow. But this has a very clear geometric meaning. What this is saying is that, let me demonstrate it on these examples. Maybe just these two examples. So what does the zero set of this polynomial look like? Well, it's a set x1 equals 1 over x2, so it looks like this, right? Now what that condition is saying is, if you look at any line whose direction is in the positive orthant, it must intersect twice. And that's indeed true, right? You take any line, it intersects twice. So in this case, the line is passing through some point B, and the direction of the line is this vector A. So that's good. But now if you look at this example, well, the graph of this looks like this, right? And here there are plenty of these restrictions that have no intersections, they have no real roots. So geometrically, real stability is a statement about real rootedness of all restrictions in the positive orthant. They have to intersect this variety of the polynomial in the right function. Okay. So these are some examples in the definition. Are there any questions about the definition? Yeah. Any questions? Okay. So now I want to present a very important example. Which is really the most important example. It's shocking how important this example is. This will come up in like all three lectures. So here's the example. Suppose I have n d by d positive semi-definite matrices, a positive definite matrix. So what that means is that all eigenvalues are positive and their matrices are Hermitian. Let's say real symmetry. It was also good enough. Okay? So suppose I have n matrices like this. Then I can define the polynomial, and suppose I have one more symmetric matrix S. Then you can look at the polynomial P of x1 through xn equals the determinant of x1 a1 plus x2 a2 all the way to xn an plus s. So that's a real polynomial. Right? This is real stable. So this is a very large class of polynomials that are real stable, of which almost all, like most useful examples are somehow derived from this. Okay, so let me explain why this is real stable.
Nikhil, maybe you could you explain again this positive definite? I'm not sure if everybody remembers.
Okay.
And
so
if
positive
this is
definite. Okay, so these are square matrices.
Yeah.
They're symmetric, and they're invertible. So they have d eigenvalues. The eigenvalues are all positive. That's what it means. Okay, maybe I should say what's important about positive definite matrices. the most important thing about positive definite matrices, according to me, is that they have square roots. Okay. So if you have a positive definite matrix, well, it's symmetric, so you can diagonalize it like this. You can write it as, okay, I'm not sure what people prefer, but let's write it like this. Right? And because it's positive definite, all these eigenvalues are strictly positive. So what that means is you can define its square root just by taking the square root of the eigenvalues, and it's the square root. And it's also invertible because these are strictly positive. That's the fact I'm going to use. Any questions about positive definite matrices? Okay. Okay, so why is this real stable? So what's the proof for this example? Well, okay, let Z be some vector in the upper half plane. So let's write it as A plus IB, where B is strictly positive and A is Rn. Okay. So now I need to prove that P of Z is not 0, right? Because all its entries are strictly in the upper half plane. Well, what is this? So this is determinant of summation, A plus IB, okay, AJ plus IBJ times AJ plus S. That's just what it is, right? It's plugged in. Okay, well now I can, pull the sum out. So this is determinant of yeah, good. So this is determinant of summation AJ, capital AJ, plus S plus I times summation BJ AJ. Okay. Okay, one more factor of positive definite matrices. If you add a bunch of positive definite matrices with non-negative coefficients, you get another positive definite matrix. So this is positive definite. So let's call this matrix M. Okay. And this is some symmetric matrix. Let's call this matrix H. Okay, so now, I can just do all the steps. I can write this as determinant H plus I times square root M times square root M. And then I can pull the square root M out on both sides. It's invertible. This is determinant of M to the minus half H M to the minus half plus I times identity. There's an I here, right? Times determinant of M of N.
Maybe you could pull the board a bit.
Oh yeah, that's what. Okay. So I've just pulled. This M has an invertible square root, so I just pull it out. I get this. Okay, but now this is the characteristic polynomial of this matrix evaluated at minus I. Let's write that. So this is equal to the characteristic polynomial of the matrix M to the minus half H M to the minus half evaluated at the point minus I, the whole thing times the determinant of M. which is not 0, by the way, because it's a verb. Okay, but that's a symmetric matrix. So this is not 0. Okay? The eigenvalue symmetric matrix are real. This is not 0. Because this is symmetric. Okay? So that's the most important example. So are there any questions about this? Who's lost by this calculation? Okay. Do you have a particular thing that's bothering you? No.
So why the last equality holds? Why this is this?
This one?
Yeah.
So I just defined the characteristic polynomial of matrix is just x times identity minus the matrix, right? So m to the minus half times m to the minus half. That's what I mean by characteristic polynomial of matrix. Okay, I'm sorry. I lost minus. It should be minus 1 to the negative. So literally, if I plug in minus I here, then this is I times identity plus this matrix, which is what's written here. So I'm using the fact that the characteristic polynomial of a symmetric matrix has real roots. This is ultimately a consequence of that. Any other questions? Okay. Okay. So those are the examples. Now, I want to move on to what are the good properties of this class of polynomials. So what are the good properties of real stable polynomials? So this is similar to what we did for real rooted polynomials. We proved that certain things like differentiation preserve real rootedness. Now we'll do the same for real stability. Okay. So there are some pretty easy ones. Like one is, so let's assume P is real stable. Now we'll write down a bunch of operations that preserve the property of being real stable. So one simple property is, again, reversal. It's like reversal. So if I look at P of minus 1 over x1, xn, where I have x1 to whatever its degree was. So I replace x1 by minus 1 over x1, but that now it's not a polynomial anymore, so I multiply it by whatever the degree was to make it a polynomial. Then this is real stable. Okay, why is that?
Why is there a minus?
Yeah, why is there a minus?
If x is in the upper half, then 1 over x is in the lower half, so minus
Exactly.
is to put it back in the upper again.
So if x1 is in the upper half plane, then minus 1 over x1 is in the upper half. Okay, that's a nice one. Another sort of easy one is what I'm going to call diagonalization. If I have a polynomial and I replace all the variables with one variable, this is, well, real rooted actually, so this is a univariate polynomial. That's just because I can just plug in the same number in the upper half plane. That's easy. If I have any number that's in the upper half plane, and I plug it into one of the variables, well, I get a polynomial in one less variable, but that's also real stable, because this is already in the upper half plane. This is easy.
Then each polynomial may have complex coefficients.
It's a good point. this polynomial may have complex coefficients. Okay. So it's not real stable, it's just stable. Okay, I'll get back to you're right. The case of this I really want to use is A is on the real line. I'll get to that in a moment. But okay, you know what? Let me just write the case for the real line. It's in the real line, then it's real stable. The proof of this, let me now tell you, is if you have a number A on the real line, let's suppose A is a number on the real line, you can choose a sequence of numbers AN approaching it in the upper half of it. Now for each of those ANs, I have that, so I'm writing the proof of this last property. I have that P of AN x1, x2 of xn has, okay, it's not real, it's complex, as you pointed out, but it's, I'm just going to call this stable, which means it satisfies the main property here, that when you plug in other things in that property, it's not 0. Okay? So, in particular, I'm now going to appeal to a fact, which I'm not going to prove, it's basic complex analysis. The fact which I'm going to appeal to, which maybe I'll just write over here, here's a fact. Fact is, if you have a sequence of polynomials are real rooted and they converge to some other polynomial in the sense of coefficients, then either this limit is identically 0 or it's real rooted. But taking limits preserves real rootedness. These are all of some bounded degree. That's important. These are all polynomials of the same degree. So limits of real rooted polynomials are real rooted. In particular, what that means is, according to this definition, it implies that limits of real stable polynomials are real stable. So then, a limit of these polynomials is this polynomial, which is real stable. Okay, so maybe I'll add this fourth property, which is taking limits. And this is why I needed to add 0. You could take some limits and get 0. One of the reasons I needed to add 0. And so this limit allows me to prove this thing that if I plug in a real number, I get another real stable. Okay. Let me okay, close under taking limits. Let's write some more properties here. The fifth property is this closed under taking partial derivatives. So d by dxj, d is real stable. So this is a generalization of this fact that differentiation preserves real rootedness, partial differentiation preserves real stability. Okay, so what's the proof of this? Well, okay, so I've assumed P itself is real stable. And let's say I'm differentiating with respect to, okay, so let j equal 1 without constant generality. So let's say I'm differentiating the first variable. So now, what do I need to show? So I'm going to fix some point z2 through zn in the upper half plane. So I'm not going to fix the first variable. Now, I want to show that the polynomial z1 maps to the derivative partial x1 p applied to, okay, let's call this t. T maps to let me, good. So this is the partial derivative as a polynomial. So I differentiate first. I plug in t into the first variable, and then z2 through zn, which are fixed in the other variables. So to show that this is real stable, I need to prove that this univariate polynomial has no roots in the upper half. Right? That's what it means. So I want to show this thing has all roots in the lower half plane to the root. Has no roots in the upper half. That's equivalent to showing that this is real stable, because I fixed everything else in the upper half plane. I need to show that, if I fix this in the upper half plane as well, this is not zero. Okay, but this is actually not bad, because so what do I know? So I know that this polynomial t goes to p of t, d2, d3, dn. This has all roots in the closure of the lower half plane. Why do I know this? Because P is real stable. That's the definition of real stable, right? Okay, but now I'm kind of happy, right? So let's call this polynomial Q of P. Well, if this polynomial is Q of P, this polynomial is literally Q of P prime. I just differentiated in first coordinate. So this polynomial is Q prime of P. Okay. Okay. So what am I going to do? Use the Gauss-Lucas test, right? So by Gauss-Lucas, the roots of Q prime, which is this thing I care about here, are contained in the convex hull of the roots of Q, which are contained in the closure of the lower half plane. So this is all contained in the closure of the lower half plane. That's it. So, I mean, this is another technique that's very common here. The point, I'm only interested in differentiating one variable, so I can fix all the other variables in advance. And then this just becomes a univariate polynomial problem, which is solved by Gauss-Lucas. That's why I did Gauss-Lucas, so I could, prove this. And for this, you really need to work with polynomials with complex coefficients, right? Because when I plug in numbers in the upper half plane, this polynomial Q that I get, Q of T, this actually has complex coefficients, because these are complex numbers. So I really need that when you differentiate a complex polynomial, you know what happens to the roots, this convex coefficient. Okay. So that completes the proof of property 5, the differentiation to the Okay. So these are the basic properties. There's one more property. Okay, so are there any questions so far about this? Okay. Okay, good. So really the beauty of real stability, so these are the basic properties, but the amazing thing about real stability is that there is a characterization of all linear transformations preserving. Okay. So I won't tell you what that is, but the space of transformations that preserve this property is very well understood. And I want to talk about one very important linear transformation that's going to keep coming up, that builds on these, which preserves real stability. So this is this linear transformation that's called the multi-affine part. Okay. So map. So map is a linear transformation from the space of polynomials and n variables of degree at most 3. So this means the degree in each variable at most. Well, you know what? I don't even really need this. So it's a linear transformation from the vector space of polynomials and real polynomials and n variables to defined as follows. It's what it sounds like. It stands for multi-affine part. What it stands for is the map of a monomial. So you have Z1 to the B1. Well, let's not call it B1. Alpha 1. B2 to the alpha 2. Bn to the alpha n. So that's what a monomial in this vector space looks like. What map does is actually very simple. It's 0 if any of these exponents is bigger than 1. And otherwise it just leaves this term. It just kills all the non-affine terms. Otherwise. So that's a linear transformation. I extend by linearity from these monomials.
So Z1 times Z2 is affine.
Z1 times Z2 is affine, yeah. So it needs to be linear in each variable. So the degree of the whole thing can be whatever, but it needs to be linear in each variable. Okay, so is the definition of map clear? So now the claim, which, so I'm running short on time, so we'll see if I have time at the end to prove it, otherwise it will be an exercise tomorrow. The claim is that map preserves real stability. You take any real polynomial, if it's stable, you kill all the higher order terms. I mean, in this sense, you get another multi-affine real stable. That's going to come up a lot. Okay, but now finally with all this preparation, let me prove theorem R. That the matching generating function is real rooted. So all of this stuff was done just so we could prove that. It will also be used tomorrow and day after tomorrow. Right. So any questions about these properties or that? Okay, so let's do now proof of theorem R. Okay, so I'll leave this here. I'll just use these two boards. So theorem R was that, let me just write it again. It was that this polynomial, you're given a graph, you write the matching generating function. Is real rooted. That's what theorem R was. Okay, so what's the proof? So I'm going to arrive at this polynomial by playing around with some real stable polynomials and modifying them using these operations to arrive at this polynomial. So what's the first step? Well, so I'm given some graph G, right? The first step is to consider this polynomial. The product over edges in the graph. Okay, so let's say the graph is B1. Right, look at all the edges, and I multiply the polynomial 1 minus xi xj. I claim this is real stable. Okay, each of these is already real stable, but that was one of our examples. And a product of real stable polynomials is real stable. So this is real stable. Okay, so now I'm going to apply math. So what's the multi-affine part of this polynomial? Well, when I expand this out, I'm going to get map of. So when I expand this out, each monomial corresponds to a subgraph, right? Because I choose a subset of the edges. So I'm going to get map of summation over all edge subgraphs F of graph E. And what am I going to get? I'm going to get the product of product over all edges or in this edge subgraph. I'm going to get xi, xj, and then there's going to be a -1 raised to the number of edges in the subgraph. So which subgraphs are going to survive this map? Matching space. So if you have any vertex that appears twice, it's not multi-affine. So if you do this, what do you get? You get sum over all matchings of all sizes -1 to the size of the matching times the product of all vertices in the matching. And this is also real stable because map preserves real stability. Okay? But now, so this is a multivariate polynomial. Okay, I should say, what are the variables? The variables are the vertices, right? Okay. Now I'm going to apply some more of my operations. So now I'm going to, so step 2 is to apply map. Step 3, so this is an n variable polynomial, let's just make all the variables the same. That was my first closure property, right? Second. Step 3 is by property 2, if I make all of these just x, I get that this polynomial, sum over all matching, -1 to the size of the matching. Now, if the matching has size, if the matching has some number of edges, I'm going to get x to the twice that number of edges. So x to the 2 is real rooted. It's not quite what I want to get, but it's actually almost there. So now, maybe the next thing to observe is that this is a polynomial in x squared, right? So, well, it's actually a polynomial in minus x squared. What polynomial is it in minus x squared? It's the matching generator. Okay, there's one more little thing I need to do. The matching generating function is a polynomial with all non-negative coefficients. So, okay, certainly all of its real roots are negative. So because this is a polynomial in x squared, its roots are symmetric about 0. And what this is saying is that the roots of this polynomial mg are minus the squares of those roots. So this is actually just saying that mg itself is real root, which is what I want. Okay. Okay. So
could you explain this last part?
Explain the last part. Okay. So. Okay, so maybe let's give this polynomial a name. Let's call this polynomial, I don't know, QG of x. So this has real roots, right? So this is a polynomial of degree, okay, I'm sorry. You know, I should have been clearer. This sum is still over matchings, so, okay, I'm sorry. Are you talking about this step? Let me explain this step also. Okay, so this is sum over all matchings right now. Let me just collect all the terms of some degree. If I collect all the terms of some degree, I get sum over k minus 1 to the k, x to the 2k times m sub k. Okay, so I missed that term. M sub k is the number of matchings of size k. So I group together terms of size k. And now I've proven that this QG polynomial is real rooted. Right? Okay, so what are the roots of QG? Well, so QG is a polynomial that is actually a polynomial in x squared. So the roots of QG are symmetric about 0. There's some plus or minus lambda 1, plus or minus lambda 2, all the way up to plus or minus lambda. I suppose the degree of this is going to be, well, the degree of this depends on whether or not it has a perfect matching. But let's say lambda n over 2, let's say it does. Okay. Okay, so this polynomial has real roots. Right? Now, really what I'm doing between here and here is a change of variables, right? So if the roots of this, yeah, okay, so maybe let me do it in steps. So this is real rooted, right? Okay, but now because the roots occur in conjugate pairs, I can, this implies that QG of x equals some polynomial. I mean, okay, let me think of the best way to explain this.
Isn't that the case that the roots of this polynomial MQ is just lambda 1 square, lambda 2 square, and so on?
Yeah, that's what I'm trying to say, but I'm trying to explain it in a further step.
But
It's a change of variables.
yes, and that's finishes the proof, isn't it?
Okay.
Because
So,
they're real, so it's real rooted.
right. Okay. I see. So what you're saying is that that this is mg of minus x squared, and so these are real.
Yes.
Uh-huh.
So lambda 1 square and lambda 2 square and so on are also real, and they are roots of MQ. So MQ is real.
Okay. Good. Okay. So if this QG has roots lambda 1 and so on, then this means that lambda 1 squared actually minus.
Yes.
So minus lambda n over 2 squared are roots of just mg of x squared. Okay, thanks. So this is mg of minus x squared. Okay, maybe I'm over explaining, but okay. Does that make sense?
Yeah, I think if you write down QG of x as a product of x minus lambda 1 times x lambda plus lambda 1, and then multiply those things, then you
Okay,
get
so you're saying you can factor this as product of x squared minus lambda I squared.
yeah. So now you see.
And now you substitute. Okay, thanks. Okay, so because of this change of variables, the real rootedness of this implies the real rootedness of mg of x itself, which is the thing we wanted. Okay, so I have 3 minutes, and I was going to prove the real rootedness of map, the fact that map preserves real stability. Instead, I will leave it for the course of the class tomorrow. So the reason I wrote all these properties down is that you can prove that map preserves stability in a few lines using these properties. And actually, it's a good test of everything we did in this lecture. So
Okay.
that's it.
Thank you.
Yeah.
In the theorem, you assume that the number of vertices is even.
Yes.
Is it necessary?
No, it's not necessary. It's just there because I don't. Yeah. It's not necessary. Any other questions? Yes.
Anything that we could use as notes or reference?
I will, yeah, let me post some notes or reference. I haven't posted any yet, but I'll post some notes on the webpage or whatever.
So tomorrow at 2:15 we continue with the lecture.
Yeah.